about determinantal representations.
So the goal of my second talk is to explain in more detail what the Lex conjecture said, how Helton-Vinnikov proved the Lex conjecture, and what the status is of this generalized Lex conjecture business that we already saw yesterday in Michel's talk. So this is all about this topic of determinantal representations, and we'll mostly talk about symmetric ones. By the end, we'll also talk about Hermitian determinantal representations. And so a determinantal representation of a homogeneous real polynomial is an expression of this polynomial as the determinant of a matrix, where every entry of this matrix has to be a linear form, a linear polynomial in the variables x1 up to xn. And everything is homogeneous for me, so the entries of the matrix have to be linear forms, and the result will be a homogeneous polynomial. And such a thing, for example, can look like this. So this is a determinantal representation of the second order cone, essentially with this extraneous factor. So maybe the goal is I would like to find a determinantal representation for the second order cone. And then for some of you, that's sort of easy to see that the determinant of this matrix is equal to this. The simplest argument, I guess, is using Schur complements. You can do induction along, expand along the first row or something. And you'll see that the determinant is this polynomial. So already here, right, so first of all, this is a determinantal representation because this matrix is filled with linear forms. All of these non-diagonal entries that I didn't specify are equal to 0. Right? So, but even here, as you can see, there is this extraneous factor of a linear form. Why is that? We'll get back to that. So you can expect one. You start with a quadratic. You would like a 2 by 2 representation, right? And that's not possible. It's also an exercise, but in general, for large n, it's not possible. It's an open problem what the smallest size of a matrix is in this example, which I think is a particularly interesting example. Not that the second order cone is maybe, there are, not from an optimization point of view maybe, but from the point of view of being able to prove any kind of lower bounds for an explicit polynomial. It's just we don't have any good techniques. If I hand you the polynomial and I want explicit lower bounds for this polynomial, we don't have any good techniques so far to prove any. So the smallest size of the matrices that give a determinantal representation of this polynomial up to some extraneous power of the variable x0 is unknown. Even for n equals 3, say. I guess even there is a decision problem that we don't know. All right, we are particularly interested, as we already saw yesterday, in what is called a definite determinantal representation, which simply means there is a value, there's a vector e. If you specify all of the xi to this e, you get a positive definite matrix. It's easy to see that this is a definite determinantal representation. You can plug in 1, 0, 0, 0, and you get the identity matrix. So this is a definite determinantal representation. We like them especially because we can do this computation often enough, because it's the mother of all hyperbolic polynomials, right? We have a definite determinantal representation. So suppose, let's just do this again, even though I think we've done it twice already. So suppose it's definite at a point E, and the polynomial P is the determinant of A. I want to show that P is hyperbolic in direction E. Okay? I look at P of x minus t times E is the determinant, so it commutes with plugging into the matrix first and then expanding the determinant. That gives you the same, or if you first expand and then plug in this parametrized line. Now I use that this is homogeneous of degree 1, so it's filled with linear forms. So this is the same as the determinant A, you plug in x, minus t times A, you plug in E. And now I use definiteness to show that this is essentially the characteristic polynomial of a symmetric matrix. Right? So if A of E is positive definite, I can factor this as B transpose B. where B is also a D by D matrix of full rank, and then this is the determinant of, I have to do it right, let's see. So B transpose, I want to pull it out, so there's a B transpose here, then there's a B transpose inverse, AX B inverse minus T times identity times B. Do this right? So if you multiply this out, you get A back, and there you get B transpose B. And now you know you pull out things. This is the determinant of B squared, which is just some constant, non-zero, times the determinant of AX minus T times the identity. Oh, there, sorry. B minus T, B inverse. This is still a symmetric matrix, so the roots are real, and this is a hyperbolic polynomial. So that's really one of the ways to think about this in various ways. First of all, it's an algebraic certificate that this is a hyperbolic polynomial. You can verify this identity by interpolation, for example, and then you just have to check the definiteness at the given point. You can think of this as an algebraic certificate that the polynomial is hyperbolic, or you can think of it as a source of examples of hyperbolic polynomials, and so on and so forth. Okay, so we just did this computation. Then the Lex conjecture was around. So the Lex conjecture says in the special case, when we look at polynomial in 3 variables only, this is the only way you can get a hyperbolic polynomial. So every hyperbolic polynomial of degree D in 3 variables has a definite symmetric determinantal representation. And here I make some simplifying assumptions that don't really matter, right? I do a linear change of coordinates to make sure that my point E is the point 1, 0, 0. And then I know because P is supposed to be hyperbolic, it's non-zero at the point E, I rescale the polynomial to be 1. So these are some things I can arrange without loss of generality for every hyperbolic polynomial. I make these assumptions because then the determinantal representation is particularly nice, and it's kind of obvious that it's definite, right? So if these 2 assumptions hold, then I can make one of the matrices the identity, and it's the coefficient of X. And then there are 2 more, just real symmetric matrices, A and B, such that P is the determinant of this real symmetric definite linear matrix pencil. And we will attempt to discuss the proof of this. It's easier to prove, a lot easier to prove, if instead of real symmetric, you assume real Hermitian and definite, or real Hermitian doesn't make a lot of sense. Hermitian matrices instead of symmetric ones, so you want A and B to be Hermitian. They still have real eigenvalues, it's still sort of, the computation works out, but the proof is a lot easier. So on the last slide, I hope I can give you a sketch of the proof where for this theorem with Hermitian instead of symmetric. One thing that's remarkable about the theorem is you don't need any extraneous factors here. Polynomial has degree D, and I find matrices of size D by D. It's just on the nose correct. So that's also another hard part of this theorem. Then yesterday we saw hyperbolic programming and hyperbolicity cones, and maybe a question is how hyperbolic programming and semi-definite programming relate. And this theorem gives the answer for 3-dimensional hyperbolicity cones. They're exactly the same as 3-dimensional spectrohedral cones. And the degree of the polynomial gives you the size of the matrices, where everything is nicely bounded and the same. So, but if you want to generalize this, you have to deal with these extraneous factors. And so one way you can certify hyperbolicity, and you can attempt to write a hyperbolicity cone as a spectrohedral cone, is by finding a definite determinantal representation, not of the polynomial itself, but of a multiple of the polynomial. So I want to show I have a hyperbolic polynomial P, and I want to look at the hyperbolicity cone. I want to show it's spectrohedral. Then the algebraic reformulation of this statement is the following. I'm looking for a hyperbolic polynomial Q, such that the product Q times P has a definite symmetric determinantal representation. But I need the side condition. This is really a tough one. This is a hard condition, that the hyperbolicity cone of this extra factor contains that of P. We saw in Michel's talk yesterday, it's not so hard to prove, that the hyperbolicity cone of a product is the intersection of the cones. And if I don't want if I'm interested in the hyperbolicity cone of P, I don't want it to change. So the cone of Q has to be larger. It has to contain the hyperbolicity cone of P. It gets even slightly worse, this statement. The generalized Lex conjecture is false, needs some extra hypotheses. So this is true if the polynomial is irreducible. If the generalized Lex conjecture holds, whatever it is, you'll see it on the next slide. You can drop this, but if not, it's not clear that you can drop this assumption.
Sorry, I missed. What was it? Irreducible?
Irreducible, what the definition is, you mean? It doesn't factor into polynomials of lower degree.
Okay. So you mentioned that Hermitian case is much easier.
Yes.
And it's 81 when it's put Dubrovin. The proof of Hermitian is Dubrovin.
Not sure. Yeah, maybe.
But I have the following question. Do you know of any application which needs this symmetric theorem and Hermitian is not sufficient? Because, for instance, all applications I personally know, including Cadiz and Singer, Hermitian is completely sufficient.
Up to a factor of 2 of the size of the matrix is the same, right?
Usually the thing is used to prove inequalities. Okay? Because for matrices, positive semi-definite, it's much easier. Okay? And you have the same inequalities for Hermitian as
Eigenvalues of Hermitian matrices.
Yes, the same stuff. So, for instance, all those like self-concordance follows from Hermitian the same way as from symmetric. So I'm just curious.
Yeah, it's a fair question. I don't have a good answer.
That is dimensional optimal, as you say.
Yes. Yeah. But I don't know if there's an application where you really need real symmetric as opposed to complex Hermitian.
Because all the application people refer to Helton-Vinnikov, but it's really Dubrovin.
Probably often enough to have Hermitian.
And his name is, I don't know, it's as easily spelled and pronounced.
Yeah. So let's elaborate on this extra factor a bit more, because it's slightly subtle, and it's an essential part of the generalized Lex conjecture. So for instance, if you want to compute these things, we'll see how to maybe algorithmically compute them. So I'm given a hyperbolic polynomial up here. It's a cubic in 3 variables, and it's the black 0 set. So there's a projective picture in P2. It's an elliptic curve, and it's hyperbolic if you've not seen this before, because there's a convex oval and there's another thing hanging out. So this sort of shows that it's hyperbolic with respect to points in here if you cone it. So this is the hyperbolicity cone. This is the section of the hyperbolicity cone. And you may want to have a determinantal representation of this, which is guaranteed to exist by Helton-Vinnikov's theorem, but maybe not a nice one, right? They're hard to compute. So in this example, I put the names of the authors of the paper where I took the example from. It's hard to find the correct factor here that makes this have a nice determinantal representation. And I would think of this as relatively nice. Right? The polynomials are relatively simple, the coefficients are integers, they're relatively small, and it takes some tweaking to get such a nice representation. And here you see in this picture, the hyperbolicity cone of this linear form is one of the half spaces. It contains that of the original cubic. So this is also a proof that this cubic is hyperbolic. This determinantal representation, it's definite for x equals -1, y equals 0, z equals 1. That's one point in here. But these factors, they need to show up, as you will see, I think, on the next slide, and it's sort of hard to control them and hard to find them if you want to do computations. It's hard to search over them. And I will also, on the last slide, give you a hint of where this linear form comes from. You have to choose another subtle curve here, and then this will be a line that has a meaning with respect to a curve I didn't draw on the picture yet. So the clean statement, the easy-looking one, is every hyperbolicity cone is a spectrohedral cone. That's the generalized Lex conjecture. If you want to phrase this algebraically, you have to deal, as I said, I can't say this often enough, I think, with these extra factors that have to have these very controlled properties. You have to have a determinantal representation of the product and the containment of the hyperbolicity cones. So that's the algebraic reformulation, and if you want to prove this conjecture by sort of generalizing the Helton-Vinnikov theorem, you have to find the Q and control this, which is a non-algebraic property. This is a semi-algebraic property, which makes this hard. We'll see that the sort of algebraic part was done. Mario Kummer gave a proof of this without condition 2. So the problem is really in part 2. Any questions about the conjecture? It looks very nice. It's very hard. So what kind of factors Q seem natural? So we've seen already that sometimes you can take a power of a linear form, like for the second order cone. There was an x0 to some power. So sometimes this works out, but rarely. Another very natural choice for this Q might be just the power of P. If I take a power of the polynomial itself, I don't change the fact that it's hyperbolic because I just put multiplicities on the roots along each line. And maybe that has a definite determinantal representation. That would be very nice because I would have a very controlled Q, and this condition 2 would sort of be easy to fix. That doesn't work out, but that would be a complicated example. First, maybe let's count why we need these cofactors at all if we're not in 3 variables, and that's a very simple count. What you do is you look at the following map. I need a pen. All right. So with this observation, look at the following map. You take n tuples of symmetric matrices. So this takes d by d symmetric matrices, n of them, and produces a polynomial out of this, the n variables. By doing the sort of obvious thing for us, if we don't care about definiteness, we take the determinant of this matrix polynomial. So essentially, we want to write every p in this form. We even want definite and whatnot. Let's ignore that for now. And it turns out that you get this bound on the size of the matrices for free because of homogeneity that I assume. If you multiply this out, every monomial will have degree equal to the size of the matrices. It might be identically 0, but you can't get higher degree or lower degree monomials because everything, if you do the Laplace expansion, is a product of linear forms. So you pick, from every linear form, you pick d many variables. So everything will be exactly degree d. But that's an aspect of homogeneity. So if you think about stable non-homogeneous polynomials, right, the setup is different. This really corresponds to the fact that I want homogeneous polynomials. That enforces the matrix size. And now we do a dimension count on things. We know that within this vector space, the set of hyperbolic polynomials has non-empty interior. The strictly hyperbolic polynomials are an open set. So we sort of know the dimension of the image of the map that we desire. And this is a nice map. It's a polynomial map. And under polynomial maps, the dimension can't go up. It can only go down. The dimension of the image of this map is at most the dimension of this space. And now you count dimensions. Right? So on the right, we have n plus d minus 1, choose n minus 1. And this is n times the dimension of this space, which is d plus 1, choose 2. So for large values of n, if the degree is at least 2, or for large degrees in at least 4 variables, there's just no chance that this will ever work out. Just not every polynomial can have such a representation, even without definiteness. That's just okay. So we need these cofactors for sure. We need to somehow manipulate our polynomial to even have a chance to find a determinantal representation in general. Without cofactors, it will never work. Does that make sense? All right. But what about this power approach? Well, that doesn't work for a subtle reason. And Petter found the corresponding counterexample, and it's a combinatorial argument that I wanted to briefly sketch. So again, remember from our talk first half, the basis generating polynomial of the Vamos matroid is real stable and homogeneous, so it's hyperbolic with respect to the positive orthant. So we would like this polynomial to have a determinantal representation. But for this one, no power will admit one. So how do you prove such a thing? And this is sort of a nice combinatorial argument. So the first key ingredient is that if you have a multilinear polynomial, you get something like a polymatroid from this. So this is an observation that is due to Gurwitz. Write down the year. So given a P is hyperbolic in direction E, and I collect n elements, which I call E1 up to En, in the hyperbolicity column of P with respect to E. So I choose these n elements. So if I have a stable polynomial, for instance, I can just choose the standard basis vectors, which is, I guess, why I call them E1 up to En. And you can do the following. You can define now the following function, defined by P, that takes any subset of 1 up to n to a number. So what do? P of the subset, you map it to the degree of the following univariate polynomial in T. So you take your polynomial, you plug in E plus T times some I in S EI. You expand this out, you get a polynomial in T. The degree is the number you assign to this subset. The claim is this forms what is called a polymatroid, the rank function of a polymatroid. So what's a matroid, right? Rank function of a matroid tries to model linear independence, or spanning the dimension of the span of some vectors, right? You're given a matrix, and D by N matrix, and the rank function of a matroid just takes the rank of submatrices. Given a subset S of N, you pick the columns indexed by the subset S, you compute the rank. That's the rank function for a classical representable matroid. For a polymatroid, don't take a matrix. Why did you pick only one vector assigned to a singleton? Why not just a subspace? So you associate to every element of n, not just one vector in the representable case, but you associate a subspace of some vector space. And then the rank function of the subset is the dimension of the span of the vector spaces Vi for I in S. So the important is essentially a matroid, but the singleton gets not assigned a number that's at most 1, but maybe something larger. So the axioms are the same as the axioms for matroids, for rank functions of matroids, except for this one assumption that the rank of a subset is at most the cardinality of the subset. That's the one axiom that you drop, because you assign subspaces to an element and not vectors.
By the way, the original statement was slightly less fancy, that it's a submodular function.
Yeah, okay, yeah, submodular. Yeah. That's the important axiom to check.
The polymatroid depends on the choice of vectors E1 through En?
Somewhat, yes. I mean, for example, I allow that all of them are the same, in which case
sure.
you get a silly polymatroid. But otherwise, not too much, but a bit. Okay, so you wonder which polymatroids are representable by subspace arrangements, and then you have to sort of worry about some of the properties they satisfy. And the essential ingredient here is called the Ingleton inequalities. I won't write them down. They are combinatorial inequalities that are satisfied in the representable case. And you prove them by sort of dimension theory in linear algebra. They're not a big secret if you have, but they get kind of complicated to write down. So,
They
but
have the name. They're like Bonferroni inequalities. It's like the inequalities for inclusion-exclusion formulas.
it's essentially inclusion.
I think they call Bonferronis, and you can prove them using Bonferronis. That for certain n it goes up, for certain n it's like odd goes up, even goes down.
Yeah. They only hold for representables in general. They don't hold for all polymatroids. And in the representable case, it's really dimension theory in linear algebra. And the point is that the polymatroid that you get from the Vamos matroid does not satisfy these Ingleton inequalities. It is not representable in a strong sense because this is a certificate. You can write down, you can pick subsets, and they will not satisfy Ingleton inequalities. But if it had a determinantal representation, or if even some power had a definite determinantal representation, so you would have determinant some xi ai. It turns out you could write down a representation of this polymatroid by the following subspaces. So this is a definite symmetric determinantal representation. Then if you set the subspace to be the range of the matrix. And this would be a representation, a realization maybe, what's the word people use? I'm not sure. Of the polymatroid associated to. The power. Well, you have to check. It's a multiple of the polymatroid defined over there. And that can't be true because it still doesn't satisfy Ingleton inequality, so there cannot be a realization of this polymatroid, and this would be one. So why is it plausible that this would be the right thing? It's not too hard to see because if it's definite and stable, so all of the AI would be positive semi-definite matrices. So you can do sort of this degree counting, that this gives you the right degree because you add up PSD matrices and the rank behaves nicely if you add up PSD matrices. So that's roughly how you argue that this would realize actually the polymatroid. Because all of the AIs would be PSD, and then degree cancellations don't happen as badly as they otherwise can. So it's really this connection to combinatorics, to the Ingleton inequalities, that makes this counterexample work out. So you cannot always use powers of the polynomial. You really need a mysterious cofactor, and you need to control the...
Actually, it's a little bit stronger. Because you not only have impossibility for R. You also, for instance, you have freedom to tweak positive coefficients. So say you start with your polynomial, and you can tweak positive coefficient.
They all have coefficient 1, right?
No, some coefficient will be 0. This homogeneous polynomial.
Oh yes, yeah, sure. I mean, the support is fixed.
You can tweak even positive coefficients. And take power. In what that won't give you the thing. Because the degree thing depends only on the support.
Yeah. It's true, but being stable depends a bit on the coefficients, right?
No. Okay, you have your polynomial, okay, and you ask, so, of course, but you start with your polynomial stable, and you even don't care whether the tweaking will destroy stability. So it cannot because you want to have that. So you tweak, you're allowed to tweak coefficients and take power. And even that won't allow you to get.
Sure. I mean, if there isn't one, you can.
Because again,
Yes,
degree
you can put
function
up.
depends only on the support, not on the actual coefficients.
So this is a very nice counterexample, which tells us a lot about these cofactors. Namely, we need to really worry about them. You can sort of, if you want, you can tweak this example a little bit. This is degree 4 in 8 variables. If you stare at it long enough, you can get an example degree 4 in 4 variables. Let's not worry about this too much for now. All right, so what do we do? How do we find cofactors? How do we find determinantal representations? And there are some curious facts. If you have these definite determinantal representations, some things tend to become sums of squares that have no reason to be, right? And so one of these curious facts, for instance, for multi-affine stable polynomials, here are the same polynomials again in Petter's theorem that show that it's stable, right? Polynomial, if it's multi-affine, is stable if and only if all of these are non-negative. So we have non-negativity of these polynomials in the stable case. If we also have a definite determinantal representation, they suddenly also become squares of polynomials. It's a sort of matrix identity computation. It's relatively straightforward. But it's a very curious, I mean, first of all, they don't have a reason to be a sum of squares. And to be a square is even more special. Is one of these curious artifacts. There are more of them, though. So, for example, in another paper, it was observed that these Hermite matrices become sums of squares in this sense. So, whenever a power of your hyperbolic polynomial admits, so now it's homogeneous again, admits a definite symmetric determinantal representation, then these parametric Hermite matrices that we have discussed factor as matrix polynomials into Q transpose times Q, where the matrix Q is not square or anything. It has some mysterious size inside, some mysterious number of rows, and it's filled with polynomials in the X size also.
So it's true in general case if H depends on one parameter.
Always. For these. If you have a determinantal representation of the power. You mean?
If Hermitian positive definite polynomial matrix in one parameter,
yes,
then it can be always factored into.
Yes.
Okay. Yeah.
Yes.
I see. So this is generalization of essentially of that one-dimensional result.
In some sense. Yes.
The point is that, and one-dimensional result is actually rather direct corollary of moments theory. So
there are many easy proofs. Yes, I think you could say such a thing.
So is this a Hermite matrix of P or of P to the K? Somehow because otherwise K doesn't appear.
Oh. I think it's P. Now you make me nervous, Pablo. I think P is fine, yeah.
P is what?
Instead of, so the power disappeared. That was Pablo's question. There's no, it's not the Hermite matrix of P to the K, but the Hermite matrix of P. But I think that's fine, yeah.
So does this give algorithms?
In what sense? For what?
I mean, assuming F has determinantal representation, can we test that it is stable?
Well, if you have the determinantal representation, you know that it's stable.
Let's say you know.
If you have this factorization, you mean? Maybe can you?
No, for the first theorem, let's say you happen to prove that it exists, but I'm just saying, can you test now the stability? So for the class of stable polynomials that have determinantal representation, do we get algorithms to test that they are stable?
You mean to find the certificate Q?
Yeah, or in the first case to prove that this is a square.
If you have the determinantal representation, you can write this as a square quite explicitly.
No, you don't have it.
You don't have it, so what do you know? Do you know that these are squares?
Just have a proof, let's say.
So somebody tells you it has a
Yeah.
determinant representation. You can use a computer to find the square.
Yeah.
I don't think it gains you much. If you just have the secret information, it has one, but you don't know anything more about it. I'm not sure it helps in finding these squares. But conversely, that's maybe why I didn't get your question. If you have such a factorization, you can attempt to reconstruct the determinantal representation. And that sort of works. It doesn't quite work as smoothly as you would hope, but a modification of this idea and a lot of details is essentially the idea that Mario had to prove this. The best positive evidence that we have for the generalized Lex conjecture, if you have a strictly hyperbolic polynomial, then there exists such a cofactor Q, such that the product has a definite symmetric determinantal representation, but we have no control over the hyperbolicity cone of Q. So it's again the condition 2 that we haven't proved the conjecture yet because we don't have control about the hyperbolicity cone of the cofactor. And the motivating idea is, suppose you have such a factorization, you don't get them quite, so you use more general Positivstellensatz results, and then you get weaker things, and then you get such a Q in the end by arguing very carefully. But this is sort of the starting point for Mario's proof, in some sense. I will not comment on this proof any further. Mario will be here at some point. Ask him about it. He's happy to talk. So this is the best we know. And since then, not much progress has been made about controlling the hyperbolicity cone of Q. All right, there is an exponential lower bound for the size of these representations that you need in general. So for the size of the matrices, is a long theorem and a bit hard to digest, maybe. So the essential idea is to prove an approximation result in the Hausdorff distance. So you're given a hyperbolicity cone, and you ask yourself, how well can I approximate this hyperbolicity cone by spectrohedral cones in the Hausdorff distance of cones? This is what is meant by these eta approximate spectral representations, spectrohedral representations. So this approximate means in the Hausdorff distance of the cones. And then it shows that if you want to do this for certain polynomials, you need an exponential size for the matrices. Right, this kappa is an absolute constant. This eta is sort of also fixed and depends on your parameters. And then you get some exponential.
D is the degree, right?
D is the degree, and n is the number of variables.
It's bad to be exponential in the degree.
It's bad to be, I think so. But that's what it is, yeah.
Kind of what you expect if you just expected the dimension counting to work out. But
Yeah. It's not too surprising that it's exponential, but it still requires a calculation. So algebraically, it means if you want to find this cofactor, it has to have large degree in general. Right. So let's maybe attempt to see how you would attempt to prove Helton-Vinnikov's theorem. And I will present a proof of the Hermitian case. This is an more elementary argument. This was worked out by Daniel Plaumann and Cynthia Vincent. It's based on something called the Dixon construction, and I will try to point out what you need in order to make this symmetric to get the full Helton-Vinnikov theorem from sort of the similar construction. I will not discuss all of the details. For example, I'm sweeping some genericity assumptions under the rug at the moment that are not explicitly stated. For this to work, as I write this down, for instance, you need that the curve defined by this polynomial in 3 variables is a smooth plane curve. And then you can do limit arguments to deal with the case when the curve is not smooth. Get determinantal representations in those cases by taking the approximation, for example, with this n path. Okay, so, but we're given the polynomial p, homogeneous of degree d, hyperbolic with respect to a fixed direction that I know beforehand. And I would like to compute a Hermitian determinantal representation that's definite at the specified point E. All right. And I will take a detour using the adjugate matrix. So I will not construct the matrix A first. I will construct the adjugate matrix of A, so the matrix of minus, right? So almost maximal minus. Of maximal. What is it called? Well, not the determinant, but the other minus. Okay. Why is this reasonable? So let me tell you roughly what's happening. So there is one very nice identity that we learn in linear algebra, and that is A times the adjugate matrix of A equal to the determinant of A is the identity. So this means something about our curve, in fact. So if you have a point on the curve where the determinant is equal to 0, then this is some matrix, right? And this is another scalar matrix. It turns out, if the curve is smooth, that this matrix must have rank 1. If the curve is smooth at this point, the determinant has a non-vanishing gradient, and the gradient is a linear combination of the d minus 1 by d minus 1 minus. So if the gradient doesn't vanish because the curve is smooth, one of the minus doesn't vanish, and this matrix has co-rank 1. Which means this matrix better have rank 1, because they multiply to 0 if the determinant is 0. So that's why I'm after the adjugate matrix, because I know that on the curve it needs to be rank 1. Be a rank 1 matrix. This is what I will use to try to reconstruct this matrix. So from this it follows that for every x, y, z with p of x equals 0, the adjugate matrix at that point has rank 1. And I assume, the curve p equals 0 is a smooth plane curve.
Is that the key assumption, that smoothness?
In some sense, if you want to do this construction, yes. I think that's the quick answer.
So essentially, the things which would prevent symmetric would be that we will have limits.
No, there are a few more details. I'll get to that in a second. So now it's a bit much to digest. Now I want to go through the following 4 steps. Let's try to see what this is. So first I need an interlacing curve. And I can pick, for example, a directional derivative of the polynomial with respect to a point in the hyperbolicity. So what I want is I have my curve somewhere. It has one convex oval, it has something else outside, and then maybe something else also. What I need is an interlacing curve, which is a curve of degree 1 less, and its 0 set sits in between. So there's an oval here, there's an oval there, and then there's some wiggly thing outside.
So the ovals must be necessarily nested if it's hyperbolic?
They are always nested if it's hyperbolic. That follows from the real roots along a line property. They sort of need to.
Okay.
It may be plausible, but not as easy to prove as it should be. But sort of the hyperbolicity condition means whenever you take any line through a point inside here, it only has real roots. So the connected components must be sort of. Yes, so they're always nested in this sense. So I need to pick this red curve, and let's say I take a directional derivative. I could pick any other. But you need this. Does it have a name? Okay, it's called A11 because it will be the top left entry of the adjugate matrix I'm trying to construct. That's why I called it A11. Now I use Bézout's theorem. I have this black curve, which has degree d. I have the red curve, which has degree d minus 1, so they will intersect in the complex plane in d times d minus 1 points. That's Bézout's theorem. Let's also assume, genericity assumption, that these points are distinct. These are distinct intersection points. There's no multiplicity counting happening here. D times D minus 1, distinct intersection points. Now what I'm going to do is I'm going to split them up into two parts. So half of the points will go into S, and the other half I want to be complex conjugate to the half I picked. That I can do because I'm intersecting real curves. So the whole set of intersection points is invariant under complex conjugation, so I can split them up in this way. Right. You picked one of the intersection points, the complex conjugate one is also one, just put it in S bar. And then you keep picking until you've sort of split them up into two halves. And from this splitting, you're going, so let's think about this. So the cardinality of S is going to be D times D minus 1 half. If everything is distinct, right, there's no other choice. And that we recognize as D choose 2. Now I want to look at the space of polynomials, homogeneous of degree D minus 1, say complex, right? Complex polynomials that vanish at these one half of the points that I picked. So let's do some numerology. I'm sort of claiming that there are D of them. Will be the first row of my adjugate matrix. Why is that plausible? So let's count things. So these have degree D minus 1, right? So there are D plus 1 choose 2 polynomials of degree D minus 1 in total. And I want them to vanish at this many points. Let's suppose they all are linearly independent conditions to vanish at these points. And then this is exactly D. So the space of polynomials that vanish at all of these points in S has dimension at least equal to D. Follows in the end that it has dimension exactly equal to D, but I can, for sure, pick D linearly independent ones in this subspace. Turns out that this is the correct dimension in the end, but for now that's not even important. Just by numerology, I know that I will always find D linearly independent polynomials of degree D minus 1 that vanish at these points in S that I've chosen. But they have to have complex coefficients now. So now we've left the real world, and now we have polynomials in complex coefficients. So, and as I said, this list of polynomials I now want to be, for mysterious reasons, the first row of this adjugate matrix I'm trying to build. Now I'm trying to fill up the rest of this matrix by this condition I have over here. I know that I want this matrix to have rank 1 along the curve. So its 2 by 2 minors must vanish on the curve. So they must be divisible by the equation defining the curve. And that's exactly what I'm writing down here. I want a 2 by 2 minor to vanish along the curve, so it must be divisible by the polynomial P. So I'm trying to construct this. So why does there exist now these things? So now we have to sort of check what K is and what we have. So there's 1, 1. This I have. This is my red interlacing curve. I have the entry 1J and I have the entry 1K. These are in my list. So now I need to find this polynomial, AJ, AJK. The fact that this exists, has the right degree, is some fact from algebraic geometry. With the genericity assumptions I stated, it follows from the fact that P intersected A11, if all of these points are distinct, is a complete intersection, for instance. More generally, if the curve is smooth, that's a theorem due to Max Noether that guarantees that this polynomial exists that I want here, this AJK. There's a unique polynomial.
Right. So the difference between this and the original Dixon construction is that the curves are tangent, right? Dixon, and in here you're.
I will comment on this in a second. So now I claim I'm happy. Now I've built, I claim I can use this for all the J's and K's to fill out this adjugate matrix. By this mysterious theorem from algebraic geometry, this AJK is uniquely determined, and I can compute it for every J and K and fill out this matrix. Now you have to convince yourself, once you have the adjugate matrix, you reconstruct a linear matrix polynomial. So there you need one more fact. And the fact of life is that if you take the aggregate of this matrix I just constructed, this will have too high degree, right? I have a matrix that is filled with polynomials of degree d minus 1. Now I take d minus 1 by d minus 1 minus. This will have very large degree. The nice thing that happens is that it is divisible by a polynomial, namely some power of the polynomial I started with. If you divide this out, this is a linear matrix polynomial, and that's the one we're after. That is the determinantal representation.
So this choice of S is presumably important in the last step? Like why is this particular choice of S?
The choice of S controls some of the properties of the determinantal representation you will get. By the way I chose it, it will make the aggregate matrix Hermitian.
Okay. But this particular reason for picking the intersection points of the polynomial and the derivative,
that's easy to see that you have to do this if you suppose you have a determinantal representation. And these are special points where something happens. So now the question is, so you can do this, you can check that all of this works out, and this is sort of some matrix lemma, you get a definite Hermitian determinantal representation. If you want some more properties, for example, you might want symmetric, right? Then you need some more control. So the problem is, if you have this splitting of the points here, you have to go to the space of polynomials with complex coefficients because you are imposing vanishing at complex points. It doesn't make, you can't expect it to be real unless the set itself is invariant under complex conjugation. Then you can find real polynomials. And that's the hard part. Because if you want this set to be invariant under complex conjugation and you want this set to be its complex conjugate, they have to be the same. So every intersection point must come with a multiplicity of 2. And that's the hard part. You need what is known as a real contact curve. You need a curve such that a red curve such that every intersection point has even multiplicity to get from this construction a symmetric determinantal representation. And that needs some serious algebraic geometry to show that such a contact curve always exists. That's why you use theta, characteristic divisor, Jacobian, blah, blah. So that's the major contribution of Victor-Vinnikov's work to this whole business, that you can choose this real contact curve, and then you can choose this as being invariant under complex conjugation, which makes this real, which makes this all real symmetric and work out nicely. But that is a non-trivial and difficult thing to prove, that this is possible. And these directional derivatives usually don't give you that. They don't necessarily produce real contact curves.
So this construction actually generates lots of different representations, right, by different choices of the red curve.
Mm-hmm.
And are they related in some nice way?
Many of them are equivalent. You can do some. What can you do? So once you have the determinantal representation, you can act on it with unitary matrices. So many of them, then, they come in finitely many orbits under this unitary action. For general curve, you have finitely many orbits of these representations under unitary action on left and right.
So does the constructions, I guess in the symmetric case, they guarantee that they're algebraic? Because the Helton-Vinnikov doesn't.
Algebraic in what sense?
Algebraic numbers, that you get algebraic numbers.
That's a good, it depends on the contact curve, right? If you knew that so you start with a polynomial with coefficients in Q, I guess, or something, right? So I think the question is, does the real contact curve have coefficients in Q also? Because then everything, then these intersection points are algebraic numbers, and then the rest is linear algebra, right? The rest is. And I think that's not clear, because it's transcendental methods that are used to show that this contact curve exists, and don't think you can control the coefficients to be algebraic numbers. Not that I know, but Victor, I guess, would have an answer to your question. I guess by... Yeah, by quantify elimination, that must exist, right? Because the real algebraic numbers are real closed fields. So such a representation is guaranteed to exist, but that even doesn't mean that in this algorithm it will work out. Right?
So is there a way of finding these A12 and so on without computing S explicitly?
That is a very good question, and I think it's open. If you get your hands on this subspace without having to compute these points, that would be extremely nice.
And this step 4 is some very non-constructive thing, or it's like you can actually see what the AJK is?
It's fairly elementary. Right? If need be, you have to do a Gröbner basis computation. This can be done. This is not a non-algorithmic secret step. So this is how you construct these. In higher, if you want to do this in more variables, all sorts of problems come up. These are not points anymore, but intersection curves or something, and then this is a very special aspect of this construction, that you here have sets of points, and it makes perfect sense for polynomials to vanish on sets of points. And so there are many subtleties if you try to generalize such a thing. There are papers that use more fancy algebraic geometry of how you can do similar things in higher dimension, but you would need more technique to be able to state these types of results. So that's what I wanted to tell you. Any questions?
So this is the outline followed by Kummer's result also? About
No. He has it in more variables, right? So you need...
okay, so it's completely different.
It is different, yeah. All right. Thank you very much.
So take like a 5-minute break?
Oh, yeah.
Or do you, what's your...
You want to talk about some of the problem, no?
how many minutes break?
Sure, why not have 5
Yeah,
break
we can
and
take
then
5 minutes break.